So in this lecture we'll describe on Compton effect, Compton theory derivations, Compton experimental verifications, properties of matter waves, J.P. Thomson experiment from Planck's theory. Okay, so let's say scattering of X-rays. There are two kinds of scattering of X-rays: coherent scattering or classical scattering, which is otherwise known as Thomson scattering, and another is incoherent scattering or Compton scattering. Coherent scattering. X-rays are scattered without change in wavelength. Okay, so original wavelength will be the same wavelength after the scattering and obeys classical electromagnetic theory. Another is Compton effect. What is Compton effect? Scattered beam consists of two wavelengths. Okay, one is original wavelength, another is the produced wavelength, and there have a difference between them. And one is having the same wavelength as the incident wave, the other is having a slightly longer wavelength called modified beam. A beam of monochromatic radiations, which is gamma rays, maybe gamma rays, X-rays, or high frequency, fall on a low atomic number substances, maybe carbon, graphite, and any other low atomic number substances. The beam is scattered into two components: modified radiations having lower frequency or larger wavelength, unmodified radiations having same frequency or wavelength. This change in wavelength of scattered X-rays is known as Compton shift, and this effect is known as Compton effect. Let's discuss the theory of Compton effect. Compton treated this scatter as the interaction between X-rays and the matter as a particle collision, X-rays, photon, and loosely bound electron in matter. Consider an X-ray photon of frequency nu striking an electron which is at rest. This photon is scattered through at an angle theta to the x-axis, and electron is recoiled with an angle phi to the x-axis, which is actually a negative angle. Okay, let the frequency of the scattered photon be nu prime. During collision, the photon gives energy to the electron. This electron moves with velocity v at an angle phi to the x-axis. As you can see, this here is an electron, okay, and this is incident photon. This is X-rays and this is Y-rays. Incident photon have the electron energy E equal to h nu and momentum h nu upon c, and scattered photon has the electron energy E equal to nu prime and momentum h nu prime upon c. And you can see the scattered photon is moving with an angle theta from the x-axis, and recoiled electron having energy E equal to mc square and momentum equal to mass times velocity having an angle phi with the x-axis. As you can see, the phi is a negative angle. Compton treated this scattering as the interaction between X-ray and the matter as a particle collision between X-ray photon and loosely bound electron in the matter. Consider an X-ray photon of frequency nu striking an electron at rest. This photon is scattered through an angle theta to the x-axis. Let the frequency of the photon be nu prime. During collision, the photon gives energy to the electron. The electron moves with a velocity v at an angle phi to the x-axis. Now, total energy before collision. What happened to the energy of photon, okay, and electron before collisions? So as you can see, energy of the incident photon is h times nu. Energy of the electron, which is at rest, rest mass energy of the electron, which is 0.511 million electron volt, and this is m naught c square, where m naught is the rest mass of the electron and c is the velocity of light. So therefore total energy before collision is h nu plus m naught c square. Now total energy after collision. Energy of the scattered photon is h nu prime, and energy of the recoiled electron is mc square. As you can see, m is different than m naught. M naught was rest mass of the electron, m is relativistic mass. So therefore total energy after collision equal to h nu prime plus mc square. Now total energy before collision equal to total energy after collision by the conservations of the energy. So h nu plus m naught c square equal to h nu prime plus mc square, and mc square equal to h multiplied by nu minus nu prime within the bracket plus m naught c square. You can see is equations 1. Now, well, if this is theta, this will be theta, and if this will phi, this will be phi, and as you can see, if this is x-axis, so as you the momentum can have its component in x-axis and y-axis, and momentum of electron can also have components in x-axis and y-axis. We can, this is the whole conservation of energy. We'll apply conservation of momentum in next slide. So total momentum along x-axis before collisions. So momentum of incident photon along x-axis is h nu upon c. Momentum of electron at rest along x-axis is equal to 0. Because before collision, electron doesn't have any momentum along x-axis because it was at rest. Total momentum before collision along x-axis is h nu upon c, because h nu upon c plus 0 is h nu upon c. Total momentum along x-axis after collision. The momentum is reserved along x-axis and y-axis. So momentum of scattered photon along x-axis is h nu prime upon c cos theta. Momentum of recoiled electron along x-axis is mb cos theta, cos phi. Total momentum after collision along x-axis is h nu prime upon c cos theta plus mb cos phi. Applying the law of conservation of momentum, momentum before collision equal to momentum after collision. So h nu upon c equal to h nu prime upon c cos theta plus mb cos phi. So taking h prime upon c cos theta to the left hand side, h nu upon c minus h nu prime upon c cos theta equal to mbc cos phi. Sorry, mv cos phi. So we'll multiply upon c, which was in left hand side into right hand side, become mbc cos phi. So total momentum along y-axis before collision is initial momentum of photon along y-axis is equal to 0 as photon is traveling along x-axis, and initial momentum of electron along y-axis equal to 0. So total momentum before collision along y-axis is equal to 0. So total momentum along y-axis after collisions, momentum of scattered photon along y-axis is equal to h nu prime upon c sin theta, and momentum of recoiled electron along y-axis is equal to negative mb sin phi, because the phi angle is a negative angle along negative y directions. Total momentum after collision along y-axis equal to h nu prime upon c sin theta minus mv sin phi. So momentum before collision equal to momentum after collisions. Then we have 0 equal to h nu prime upon c sin theta minus mv sin phi. Then we have h nu prime sin theta equal to mb c sin phi, which is equation 3. Now squaring equation 2 and equation 3 and adding that, we have phi angles that we have before in equation 2 and 3 will be cancelled out, because sin square phi plus cos square phi is equal to 1. So m square b square c square cos square phi plus sin square phi equal to h square nu minus nu prime cos theta square plus h square nu prime square sin square theta. Now m square b square c square cos square phi plus sin square phi equal to h square nu square minus nu 2 nu prime cos theta plus nu prime square cos square theta equal plus h square nu prime square sin square theta. Now m square b square c square cos square phi plus sin square phi equal to h square nu square. Actually we multiplied h square inside the bracket, minus 2h square nu prime cos theta plus h square nu prime square sin square theta plus cos square theta. So as you can know, cos square phi plus sin square phi and sin square theta plus cos square theta equal to 1 respectively. So m square b square c square equal to h square nu square minus 2h square nu prime cos theta plus h square nu prime square, which is equation 4. Now squaring equation 1, what is square equation 1 was the conservation of energy. Now m square c4 equal to h within the bracket nu minus nu prime plus m naught c square का whole square, and m square c4 equal to h square nu minus nu prime square plus 2h nu minus nu prime m naught c square plus m naught square c4. M square c4 equal to h square nu minus nu 2 nu prime plus nu prime square plus 2h nu minus nu prime m naught c square plus m naught square c4, which is equation 5. So subtracting equation 4 from equation 5, that we have m square c4 minus m square c square b square equal to h square nu square minus 2 nu prime plus nu prime square plus 2h nu minus nu prime m naught c square plus m naught c4 minus h square nu square minus 2 nu prime cos theta plus nu prime square. M square c square, just taking common, so we have c square minus b square minus 2h square nu prime plus 2h nu negative nu prime m naught c square plus m naught square c4 plus 2h square nu prime cos theta. So m square c square minus b square equal to 2h nu negative nu prime m naught c square plus m naught square c4 minus 2h square nu prime 1 minus cos theta, which is equation 6. So we have to just substitute m square c square multiplied by c square minus b square is something in terms of m naught. So we'll help of relativity theory and we'll put the relation between m and m naught by relativistic mass formula, which is m equal to m naught upon root over of 1 minus b square upon c square. Okay, so from the theory of variation of mass with velocity is given by m equal to m naught upon root over of 1 minus b square upon c square. So equation squaring equation c, just putting m square multiplied by c square minus b square equal to m naught square c square. Okay, so m naught square c4 equal to 2 negative 2h square nu prime 1 minus cos theta plus 2h nu minus nu prime m naught c square plus m square c4. So this is m naught c square c4 is in left hand side, so right hand side, so we can cancel out this. So 2h square nu prime 1 minus cos theta equal to 2h nu minus nu prime m naught c square. So nu minus nu prime upon nu prime equal to h upon m naught c square into 1 minus cos theta, and nu upon nu prime minus nu prime upon nu prime equal to h upon m naught c square into 1 minus cos theta. So now we got the result of 1 minus nu prime minus 1 upon nu is equal to h upon m naught c square 1 minus cos theta. So this is the relation of Compton effect in terms of frequency. So let's derive these equations, Compton effects equations, in terms of wavelength. So multiplied by equation C, both sides, that we have C upon nu prime minus C upon nu equal to h upon m naught c 1 minus cos theta. So C upon nu prime, substitute lambda prime, and other C upon nu is lambda. So lambda prime minus lambda equal to h upon m naught c multiplied by 1 minus cos theta. So this is exactly the Compton's effect formula in terms of wavelength. So therefore the change in wavelength is given by lambda prime minus lambda, which is delta lambda equal to h upon m naught c 1 minus cos theta. So the change in wavelength d lambda doesn't depend upon the wavelength of the incident photon. As you can see, d lambda equal to this expression doesn't have any wavelength lambda. Okay, so that means wavelength of incident photon doesn't depend upon the wavelength d lambda. Okay, and the nature of this scattering material, the change in wavelength d lambda depends only on the scattered angle. So when theta equal to 0, that means cos theta equal to 1, so d lambda will be 0. Next, theta equal to 90 degree, so cos theta will be 0 and d lambda will be h upon m naught c. Substituting the value of h, m naught and c in the formula, we can see h equal to 6.67 into 1 into 10 to the power negative 34 joule second, m naught is 9.1 into 10 to the power negative 31 kg for mass of the electron, and c is the speed of the light, which is 3 into 10 to the power 8 meter per second. So we got the result d lambda equal to 0.0243 angstrom. When theta equal to 180 degree, cos 180 degree will be negative 1. So d lambda will be 2h upon m naught c. And if we substitute the formulas, constants, so we got the result 0.048 angstrom. So the change in wavelength is maximum at 180 degrees. So this is the experimental verification of Compton effect. This is X-ray tables. This is monochromatic X-rays, and this is graphite target. This is patterning X-ray. This is X-ray detector, and these are unaccelerated X-ray. Circular table, which is this one, is circulating like this, like this. Okay. So we'll discuss the theory of experiments in the next slide. This experimental setup is shown in the last slide. A beam of monochromatic X-rays beam is allowed to fall on this scattering material. The scattered beam is received by a Bragg spectrometer, which is moving in the circular table. The intensity of beam, and the difference between the two peaks keeps the shift in wavelength. When the scattered angle is increased, the shift also gets increased in accordance with d lambda equal to h upon m naught c 1 minus cos theta. The experimental values were found to be in good agreement with that found by the formula. Compton's result at the scattering angles 0, 45 degree, 90 degree and 135 degree is shown in the following figure. As you can see, these are the four graphs for different angles for theta equal to 0, theta equal to 45, theta equal to 90 degree, and theta equal to 135 degrees. This graph is between intensity of scattering X-rays and the wavelength. There are two peaks, one is for modified beam and another is for non-modified beam, and the difference between them is what we have called a wavelength shift. Okay, for theta is equal to 0, there is no modified beam because d lambda equal to 0. Okay, and for theta equal to 45 degree, there is a modified beam. For theta equal to 90 degree, there is a modified beam, and for theta equal to 135 degree, there is a modified beam. So the wavelength of scattered X-ray become longer as the scattered angle increases. Compton shift delta lambda is 0 when nu equal to 0. What is nu? The frequency. Okay, Compton shift. Okay, sorry, this is theta. For when theta equal to 0, and Compton shift is maximum when theta equal to, this will be 135, not 135 degree, this should be 180 degree, but yes, theta equal to 135 degree, also because cos 135 degree is also negative, so this will be greater than 2s upon m naught c. Okay, so this is theta equal to 135, maximum 135 degree, and also maximum for theta equal to 180 degrees. Next we'll discuss on matter waves. Okay, the wave nature associated with the material particle is known as matter waves. De Broglie hypothesis. Waves and particles are modes of energy propagations. Universe is composed of matter and radiations. So since nature loves symmetry, matter and waves must be symmetric. If radiation like light, which is a wave, can act like particle, then materials like particle can also like waves sometimes. Okay, so as you can see, if wave can act like particles, why don't particles can act like waves? So matter has dual wave particle in nature according to de Broglie hypothesis. It has both particle and wave like nature. So lambda equal to h upon p, where h is Planck's constant and p is momentum of the particle, which is mass times velocity. The energy of the particle with quantum concept is E equal to h nu. From Planck's theory, E equal to h nu, which is equation 1, and according to Einstein theory, E equal to mc square, which is equation 2. So from equation 1 and 2, we have h nu equal to mc square, and hc upon lambda, we can see nu equal to Planck's light's velocity upon lambda. So hc upon lambda equal to mc square, and therefore lambda equal to hc upon mc square and lambda equal to h upon mc, where if the particle is moving with a velocity which is less than the velocity of light, we can write c tends to v. So we have lambda equal to h upon mv, and that's how we derive de Broglie wavelength. We know that kinetic energy equal to E equal to half mv square. So multiplied with m on both sides, that we have Em equal to half m square v square, and m square v square equal to 2Em, and root over of m square v square equal to root over of 2Em, and we have momentum equal to root over of 2Em. So substitute in equation 4 that the de Broglie wavelength, that we have lambda equal to h upon root over of 2Em. So we can put the values of h and m for electron, proton and neutron, and we have different values of lambda for momentum, for wavelength of electron and neutron and proton respectively. So just we can put the values of energy that we are providing to the particle, and also from that we can calculate the wavelength of the associated particles. So we'll discuss Thomson up experiment, which is evidence of that there is a possibility of de Broglie waves, or de Broglie hypothesis that electrons or any particles can also have a wave-like character. So in 1927, George P. Thomson's to demonstrate a diffraction pattern of characteristic of atomic arrangement of a target of powdered aluminum. This is basically a diffractions pattern of we can see more oftenly this is Fraunhofer diffraction pattern. This you can see source is there, it is source, and this is X-ray or electron, which is source, and light is coming from the source X-ray. So in terms of electron, the source is like a wave like X-rays, or particle like electrons, like we can see, or an electron beam, okay, which is throw electrons from that electron gone, which is acted as source, okay. And this is a target materials, as you can see, which is having a length 1 meter from the source, okay. And this is photographic plate or screen, which is having a distance of 10 cm from the target materials. And target materials have the thickness 1 micron. What is 1 micron? 10 to the power -6. So as you can see in the photographic plate, the radius or of the circles are equal to 1 cm. So we'll discuss more about Thomson experiment in the next. So as you can see, this is what we have, the nature of the experiment in the screen. This is the screen. As you can see, this you can see the circular wave nature, as you can see, okay. This is the circular pattern, and this is G.P. Thomson apparatus for diffraction of electrons. So a narrow beam of electron is produced by the cathode C. The beam is accelerated by potential up to 50 kilovolt. Okay. These electrons rays, after passing through a slit S, are incident on a thin foil G of about thickness of the order of 1 micrometer. The diffraction of the electron takes place at G, and the patterns is photographed using the photographic plate P. The diffracted electrons produce in the diffraction rings as shown in the diagram in the last slide. The size of the crystal unit cell can be calculated. This pattern confirms the electrons are diffracted only due to the presence of electrons and not due to the secondary X-rays produced by the electrons while going through the foil G. So for example, if foil G is removed, targeted material is removed, the entire pattern disappears. So foil G is essential for the diffraction pattern. Thus the experiment clearly demonstrates the electrons behave as waves, and the diffraction pattern can be produced only by the waves. So by knowing the ring diameter and the de Broglie wavelength of electron, the size of the crystal can be calculated using Bragg's law, which is 2 pi r equal to n lambda. So the experimental result, its analysis are similar to those of powder crystal experiment of X-ray diffractions. Okay.